All right, so now we're on to the second half of today's lecture, which we'll talk about. We're going to talk about estimation in sampling. So once we've sampled, lots of times we want to know something about the population, and the things that we're going to talk about. There's three different things that we're going to talk about: the mean, the total, and the proportion in the sample size selection. Am I good? So those oh, no problem. We just started class back up. We're just making sure. Oh, no problem. Yeah, that can happen sometimes. All right, so we are going to talk about these, and sometimes we refer to this as a point estimation. So a point estimation is we're going to estimate the actual value. In other words, we collected a sample mean. What is the population mean? Well, that's actually pretty easy. We'll talk about why this is, but if we've collected the sample mean, the best estimate of the population mean, if it's a truly systematic, proportional, a probability-based sample, then the best estimate of the population mean is actually the sample mean. All right, but what if we want to be confident that it falls in a certain range? Because the population mean is a number that actually exists, but we don't know it. Well, how confident are we that our particular sample, it falls within a certain interval that includes the real sample mean? So that's the way we express our interval estimation. So in other words, when you hear something like, the percentage of people that are going to vote for Donald Trump or Bernie Sanders, whoever's going to be the Democratic nominee, I don't know who it's going to be. I just heard that Bernie was getting the most votes right now. But if we're gonna get that, we could say this is the number of people that said they're going to vote for Donald Trump plus or minus some value, and that is interval estimation. So we're going to learn about doing that today. Okay. Now that one actually falls into this proportion. So we've got proportions, means, and totals that we're going to talk about. And that covers a lot of things that we want to know about the population. So first we need to talk about this thing. It's called the sampling distribution of a statistic, and that's going to lead us right into the central limit theorem, and then we'll get into confidence intervals. Okay, so we're going to talk about why the math works to do this, and it relies actually. We're going to end up using the same normal distribution that we saw before, but you might ask, well, what if my data isn't normally distributed, or what if I know that the population mean isn't normally distributed? And most of the time, as long as you have a sufficient sample size, and we'll show why that's necessary, it doesn't actually matter because of that central limit theorem. So let's explain that real quick. So first of all, this kind of should have gone on to the first slide, I guess, but here the goal of sampling, in our case and in most cases, is estimation, inferring the population characteristics. So we're going to talk about three today, and they're the most common ones. So what's the real mean? When I say real mean, I mean the population mean. What's the population proportion? What's the population total? All based on only having a sample. Okay. And as I said, the best point estimate for a population mean is the sample mean. For the standard deviation, it's actually the sample standard deviation as well. Okay. And how do we calculate the probability that the population mean falls in a certain interval? That's what we're going to talk about towards the end of the chapter. So intervals are important. Just coming up with a value will get us somewhere, but if we want to find out, if we want to make an estimate of how confident we are that that value is near the true value, then we need to come up with an interval. And sometimes the question is, I want to be X confident, so how big of a sample do I need to get X confident, X level of confidence? And we can answer either question. That's just a matter of algebra, right? So it's just a different unknown. So sometimes the unknown is how many samples we need, and sometimes the unknown is, more often the unknown is how confident we are based on the number of samples. Okay, so yeah, we've already established this. Because it's a sample, it's unlikely to be exactly equal to the population parameter, especially if it's a continuous number, right? If it's an actual numerical value, it's very unlikely that it's exactly the same. Okay. So the interval estimation allows us to kind of establish a range where the real value is likely to occur. Okay, that's what we're doing here. And sometimes we call that the confidence interval. So what we often say is that we're 95% confident, or the confidence interval is 95. This confidence interval, 95% of the time, if we collected a sample like we did, 95% of the time, the true population mean should be in this range. Okay. All right. So why does that work? Because that's our goal. But how does the math work? Well, this is how the math works, and we don't have to calculate it all out. But it's been observed that whatever distribution our population actually has, like, for example, we've been using incomes as an example a lot in this class so far. Are incomes normally distributed? I mean, do you hear people talking about income disparity in the United States a fair bit? Yeah.
People tend to cluster by their income.
Well, cluster spatially. I'm actually, so the spatial distribution isn't necessarily normal, but I'm also just talking about, like, if I truly randomly sampled 100 people in the United States, then the distribution, it wouldn't be the same as every other country, like, or any other country, but there would be a significant amount of people in, like, the middle class area, and then there would be, like, a few, like, really, you might have seen those things, like, if the world's population was this, then there would be one person that had, like, there's 100 people in the world, there'd be one person that had, like, $1 billion income, and then, like, the rest of the people would all have hardly anything relative to that guy, right? What I'm trying to say is the population, the incomes are definitely skewed in the positive direction. In other words, there's a cluster in middle class countries. That cluster tends to be a little bit higher, but there's still a cluster down there and a big tail out to the top. And since you can't earn zero, there's actually, I mean, you can earn zero, so you can't earn less than zero. There's obviously a big pile up, especially in developing nations. There's a bunch of people that earn hardly anything. But even in those countries, there's still some people that are wealthy and then extremely wealthy, right? I'm sure there's billionaires and probably a fair bit of millionaires in countries like India, but then there's an awful lot of destitute people. And so that is an example of a distribution that might actually be kind of similar to the Poisson distribution, or another way to maybe it's even an exponential distribution. In other words, it's high on one side and it has a big tail going out in the other direction. And so whatever our population is, it's very likely that it's not a normal distribution. Now, there are a lot of things that are normally distributed. I think I mentioned that before, but things like if I just took the temperature on the same day every year for 100 years of a city, that probably would be a normal distribution. It may be going up, like that's the climate change, but assuming we could like remove any bias like that, it's probably pretty normally distributed. And the same thing might be said with like the size of any biological feature on a human or an animal. It may be changing slightly over time, but my guess with all living creatures of that same thing, if we were to measure the size of the weight of a certain species of frog, then that would probably be a normal distribution. Now next week we're going to start talking about, well, what if we wanted to say, what if we had a hypothesis that the frogs here were heavier than the frogs over there? Okay, that's next week. But this week we're just talking about coming up with if we just sample 10 frogs here, how likely is it that their average weight represents the population average weight? Okay. All right. So somebody, or it's been discovered that even though the distribution may not be normal, if we take an infinite number of samples of that particular distribution, in other words, if we could theoretically take a sample of 10 frogs, weigh them, 10 frogs, weigh them, and calculate the mean, 10 more frogs, weigh them, and calculate the mean, 10 more frogs, weigh them, and calculate the mean. You can see we can do that over and over and over again. Then even if the true population isn't a normal distribution, that's this black line here, the red curve will be the distribution of those sample means. So that's the red curve here, and it will be normal. That's where I want to get into. Oh yeah, I had to close it because of that. So I'll just open this up real quick. This is just a really simple Jupyter notebook. You don't have to download this if you don't want to. What I'm going to do is just show you visually how this works. So all I've done here is I took a sample of the exponential distribution and I made the edge of the distribution be 4 and I made the sample size 50. And I took 1,000 samples of that population and I calculated the mean. And so what I have here are two different diagrams. This is a histogram of just one of the 50. So in other words, it's the last. So I took 1,000 samples. This is the last sample. Does that distribution look normal? No. It's higher. It's higher up here and tails off as you go. It's higher up here and tails off as you go this way. Okay. All right. So that's that. Now, then I took all of the means and put them together in one data frame, and I graphed those. And this looks a lot more normal. Again, it's not going to be perfect, but it's pretty close to normal distribution. So I can modify one of the parameters here and say, okay, well, what if I made the sample size only 5? I'm still going to take 1,000 samples, but I'm only going to make a sample size of 5. Then if I run these through, Okay, this is this is just the last sample taken. So just the last sample. Remember, there's only 5 values this time. So what it's saying is 2 of them had a value between 4 and 4.2. 1 of them had a value of about 5, and 2 of them had a value about 5.4 in the 5.4 range. Okay, and let's look at the. Okay, does that look a little less normal? Yeah, it does. You notice how we're starting to kind of see the underlying distribution, the distribution that looks more like the logarithmic distribution. So the logarithmic distribution just starts and then it just tails off that direction. So you can see that that this looks a little bit more. So if we change that to 2, actually if we just change it to 1, well, let's just change it to 2 because I don't know if it'll even work with 1. Now it looks a whole lot more like the exponential distribution where it's just going like that. Okay, so as the sample size increases, we'll change it to 100. As that sample size increases, it gets closer and closer to the normal distribution. And at 30, it's kind of close enough, is what statisticians that study this have said. Is at 30, that value is sufficient to basically mask the real distribution that's behind it, and it's always going to the mean value of all of the sample means is going to be a normally distributed value as long as your samples get over 30. So that's the math behind choosing 30. It's not like it's a magical number, but it's the number because it's approaching a normal distribution. It's the value at which point you can basically treat it as a normal distribution, 30. So what if you only got 29? Well, it's a little bit different. There is actually a way that you can do 29 or even 5. There's basically a way you can account for a value looking something different than 30. Okay. So yeah, I wonder if we did like 2,000. I got to run through all those. Yep. So it looks more normal, and it may just be that we've chosen. See, I've only chosen to bin this into 10 bins, but it looks pretty normal, and we could see that mean gets the mean should be 1 greater than this number. That's the mean of the mean of an exponential distribution is always 1 greater than the number that you feed it there. So the mean is 5. So another way to look at this is to see how close this gets. So that's the true. This is the true mean of that distribution, assuming an infinite sample. Okay. So look at how close we got. Well, if we change this way back to 5, we were almost at 5 before, and we're going to get a value that's actually pretty close to 5, right? 4.98. Not quite 5. And I think especially if we bump down this to 100, so we still got 4.99. Okay, we got 4.99. Did it again. This time we got 5.05. See, there's an element of randomness each time I run through it. 4.95. So what we're trying to do, see how this number changes, and it's not quite 5 every time. We're trying to come up with an estimate to say how often that number falls within a certain confidence of the real value. That's where we're going with the confidence interval, the estimation. Okay, so this this phenomenon is referred to in statistics as the central limit theorem. So, given the effect of randomness, if it really is a random sample or something close to a random sample, then we can determine that the sample means will fall above and below the true population mean. Okay. Provided that they are truly independent samples, the mean of all the sample means will be the population mean. So when I took this class, my professor said the mean of the means is the mean, which sounds a little confusing, but that is a more complete statement. So the average, in other words, another way to say that is the average sampling mean is the same as the population mean. In other words, if you take an individual sample, which is what we usually do, we only usually have one sample. If we take an individual sample, it may be different than the mean. But if we took a theoretically large number of samples and then calculated the mean of those samples, the overall mean, the population mean, should be the same value. And what's further is that the distribution of those sample means should be normal. And if it's normal, we can use the same math that we did last week to find out the z-score. And if we can find out the z-score, then we can come up with the estimate, because we can figure out how far off we are on a standard normal distribution and then scale it using the z-score. Okay, so that's all the math is. It's fairly simple when you boil it down like that. Okay. Now there are a few things to consider. So one thing is the sample size. The sample size needs to be large enough. Okay. This is what I just showed you basically in that workbook, but this is just showing how if the population is small, it may not be a normal distribution. As that sample gets larger, it approaches a normal distribution. Okay. So here's another little video that talks about the central limit theorem and this concept of the standard error of the mean. So the standard error is basically the variance divided by the square root of n, the square root of the total number of values that you have. And so what this is saying is how much error will there be in the sample means? Well, the amount of error in the sample means is related to the standard deviation in the population divided by the square root of the number of the number in the sample. Okay. So like in Excel, let's just say we have a value that is 5. That represents how much, well, let's just call that variance. So that's the variance in the population, is 5. Okay. So what that means, I'm actually going to, well, I'll leave it there. Okay. 1, 2, 3, 4, 5, 6, 7, 8. See if this will figure it out. Yeah. I'll go down to 30. So if that's the variance, then the standard error of the mean, in other words, how far off the mean will be, is going to equal that divided by the SQRT, the square root of that. Okay. So you see how that number starts out large and gets smaller and smaller. See, because 5. So what's that saying is that the variability of that sampling of that sample mean is going to go down the larger the population size is. So if I have 30 randomly selected points, see how much smaller the variability is in terms of the sample mean. That's the standard error of the mean. In other words, it's the average distance that any sample mean is from the real mean. That's the standard error of the mean. So if we wanted to truly standardize it, we'd make this 1. So what we're doing is saying if we only have one sample, then we could expect that the sample means could be off by as much as 1 unit. But if we have 30, the sample mean on average is only going to be 0.18 off of the true mean. So you can see once we know the number of samples and we know the standard deviation or the variance. This is the variance in that case. Which, remember, how are the standard deviation and variance related?
One's the square of the other.
Right. So standard deviation squared is the variance. So lots of times, I'll just assume that that one or the other is what's known, because if you know one, you know the other. Okay. All right. So what this leads to is that the larger the sample size, the smaller the amount of sampling error. You can see that. That's what I've just tried to show here. This is the sample size. And this is the standard error. You can see the larger the sample size, the lower amount of sampling error that there will be. Okay. All right, so what's interesting is that, well, not the only thing that's interesting, but one thing to remember, one thing to point out is that the statisticians that came up with this noticed that it was only completely true for infinitely large populations. Now, what's an infinitely large population? Well, we can mathematically look at that here in a minute, but if the population size is 500, then that's nowhere near infinitely large population size. But if it's really, really large, we can treat it as infinitely large. So if we're talking about 300 million people, then we can treat it as that. Forgot what the book says. I think the book says like a value of 5,000 is pretty close to being able to treat it as infinitely large. But I'll look that up again because I forgot what that number is. But if it isn't, if it's smaller, like 500, then we should use the what's called the finite population correction factor to weed that out. Yeah, so that's figure 8.8 in your book. This right here is the finite population correction value. Okay, yeah, I'm trying to see what it says. It doesn't actually give a sample mean, but let's look at that. So N, the big N in here is the population size, and little n is the sample size. Okay, so let's do that here. So let's just say that 500 was the population size, and then this is the sample size. So the way we figure out the FPC here is that would be the square root of, let's call this pop size. And I need to put an equal sign here. Equals, oh sorry, not the square root. Yeah, it gets square rooted in the end, but the book just has just the non-square rooted parts. I'll do that for now. So it's the population size minus the sample size divided by the population size minus 1. And because this is math, we need to put the parentheses in. And that's the finite population factor. And notice that this also decreases as you go down, but not by as much. Now, what if this was, 10, 0, 0, 0? That stays pretty close to 1. Then the number that actually gets put into the equation is the square root of that number. So that's just going to make anything below 1 go a little bit further below 1. So it gets really small really fast. So that might be a good way to look at this, okay? Actually, here, let me make this 30. That might make this make a little bit more sense, I think. Okay. I wish this all fit on one screen, but so I made my population 30. So what we're saying there is if the population is only 30, once you collect 30 samples of a population that's of size 30, there's no more finite population factor to factor into your problem. You've basically collected everything, all the information from that area, so there's no corrective factor to put in. If it's 100, you've gotten close, but there's still a little bit of a finite population. It's a multiplicative factor in the equation. So we'll show that here. Oh, well, here it is right here. So if we're trying to determine the population variance, then what we need to do is say that the variance divided by the square root of n times the finite population factor, that's what's equal to that that overall value, the standard error there. So the standard error is equal to the variance divided by the square root of n times the finite population factor. All right. So lots of times we can assume that it's a really, really big population and we don't need to do that. But sometimes we need to do that, particularly for smaller population sizes. I think there's an example in the book that actually works you through when you should do it, or in the exercise. Okay, so let's move on to confidence intervals, which is what we're going to do for the rest of today, because that's the main thing that we're trying to present today is confidence intervals. So what we need to do to get a confidence interval, we need to take the point estimate, in this case the mean, and then we need to add plus or minus the z-score times the standard error. Okay. So lots of times we need to calculate the standard error and then multiply that by the z-score. The z-score comes from the standard table. We can also do that. There's also a way to do that in Excel, so I'll show you. We'll walk through both ways. Okay. The z-score is determined. One of the inputs to the z-score is a knowledge of the confidence interval that you want to have. In other words, if you want to be 90% confident, then that's the number you take to the z-score. So you'd look in the tables, and you'd want to be you'd want to find in the tables, it'd be a little bit complicated because remember what you're looking for is the area under one half of the curve such that on either side we get 0.5. So in other words, that would be, okay, let's do that. So we only know this area under the curve, right? That area. And we want to know if that area is x, we want there to be 0.5 left over here. So how do I get that value? What's the area under half of the curve on the standard normal table? On the standard normal curve, what's the area under the whole curve? No, not the green area, just the total area. 100, right? 1 is 1. 1 under the whole curve. And we want to find out, in order to use the table, we need to find out what this area is, because the table only reports that area. Okay? So what is this area? If this area is 1, what is just this area? We know this area is 90. It's half of 90.
Yeah. Oh, you said for this you're talking about specifically the green.
I'm talking about half of the green area. This.
45.
Yeah. 0.45. Yes. So what we need to do is find that on the table. And these are, remember, the table, I'm talking about the table on 303. The table, those are areas that are listed inside the table. So if we find the value that's closest to 0.45 that I can find is kind of on the middle of the table. And if I go out on the z, I see that it's 1.6. And if I go up, I see it's 1.65. Okay? So 1.65 is the z value that's associated with a 90% confidence interval. So I would take 1.65 and multiply that by the standard error, and then I would add and subtract that value from the mean to get the confidence interval. Okay. Now,
Confidence intervals in like standard deviations, or is it just under 1? Like
the confidence intervals are in the units of whatever the units are in. So if the mean is in, like if the mean is feet, then the confidence interval is in feet. Now, as I said, lots of times nowadays we have software, we don't have to look up the value on the table. So I'm going to show you how to do that. That's actually what I talked about is in the table, in the class data table. The addition to the class data table is this worksheet for random or systematic samples. I didn't spell systematic right. I'm just going to write, well, it doesn't really matter at this point. Okay. This example is actually in your book. The values here, chapter 8. I'm using the same data that's in table 8.3. And you'll notice that the numbers aren't exactly the same. They do some rounding. But the secret is this. The formula uses this confidence dot norm. Okay. So what I put in here is the mean. The mean is 9.6 in this example. That's over on page 122. I got that from there. So it's the journey to work example. So the average time to work is 9.6 with a population standard deviation of 3 minutes. Okay. So I took 50 samples and I want a confidence of 90. So the way that I do that is I first calculate the width of that confidence interval, and that is what it requires. The first thing that it requires is the alpha. So in other words, I don't need to give it a z-value. It figures out the z-value. It looks up the table for me, but I need to tell it how confident I want to be that my my confidence interval will encompass the true population mean. So in other words, if I put 0.90 here, then what I'm saying is that if with any given sample, I'll probably be right 90% of the time. That's what I'm saying there. So you could see that the width, it's really 1/2 of the width, because it's just one side of the thing. So that's 1/2 of the width. The full width is right there. Okay, and then I can calculate the lower bound as, see how that is the mean minus the half of the width, and then this is the mean plus the width. So then I have a confidence interval there. And you can see this right now, these numbers right here pertain to the second line on the table. And you can see that the number of standard errors, the Z value, is 1.65 that they looked up. But we know in reality that it's actually not 1.65. It's just really, really close to that. That's the closest value that appears in the table. And so our number using in Excel is getting the exact value. And that's why when you look at the width, it says 1.40, but mine says 1.95. If I change this, oops, wrong way. If I change this so I only looked at 2 decimal places, I would get the same answer that they did. See that? Okay? So that's how you do it using Excel, using this confidence.norm function. And you can use confidence.norm function as long as you as long as your samples is over about 30. So let's play around with this a little bit. What if my samples, what if I'd actually taken 100 samples and I still got the same mean and population standard deviation? How would you expect that to change the confidence interval? You think it would make it wider or narrower when I change it to 100? Remember what happened to the standard error? Because it's just Z times the standard error, or yeah, the standard error of the mean. So it's Z times the standard error of the mean. Remember what happened as the sample size got larger? What happened to the sample error in my other spreadsheet? In this spreadsheet right here. This is the standard error, and as the sample size increases, the standard error gets smaller, right? So here, when I make this 100, it already switching it back and forth. It actually made that bound smaller. See how it's only about 1 plus or minus. What's about plus or minus half? So the interval is only 1 now. So if I change this back to 50, see how it went back? It got larger. So the number of samples that I take is going to give me a narrower confidence interval given the same confidence. Now what if I decide I better not be wrong? I really can't be wrong. I can only afford to be wrong 1 time out of 100. So if I change this to 0.95, what do you think that's going to do to my confidence interval? Well, if my confidence interval gets smaller, then am I more or less likely to get the true population mean? Less likely. So my confidence interval needs to grow larger if I want to be wrong less often. See how that works? So now, see, I changed that up to 1.9. Oh, I meant to say 99, but still, now it's gone up to 2.19 is the width, the entire width. So what I'm doing is saying, well, the true population mean, I only know my sample means 9.6, but if I want to find out if I want to get an estimate of the true population mean, I need to say it's between roughly 8.5 and 10.7 in order to be pretty confident that it's in there. In other words, that value be in there 99 out of 100. Now, that's usually the highest that people go, but theoretically I could say, what if I only be run once in 1,000? Well, now I can see my lower bound needs to be 8.2 to 10 to 11. So basically about 8.2 to 11. So it keeps getting larger. If I want to be more confident that the real value goes in there, then the confidence interval is going to be larger because it has to include any mess up that you might have had. So that is something that you should keep in mind, okay, how that works. So the number of samples causes your confidence interval. As the number of samples goes up, the confidence interval gets tighter. As the confidence level goes up, the confidence interval gets wider, gets bigger. So as this number gets bigger, the confidence the interval gets smaller. As this number gets bigger, the interval gets bigger. Okay. So those are your trade-offs. You can either decide you don't care about being as confident, or you can go out and get more samples. Those are the trade-offs in this type of thing. So you can fix any of these. So you can decide, I want my confidence to be, I want to be right within 2 percentage points. So you could fix that, and then you could determine what samples you wanted to get. You'd also have to define a confidence interval. So if you define any two of these three, samples, confidence, and upper and lower bound, then you figure out what the other one needs to be. Right? So you fix two. So the way this spreadsheet works is you're fixing these two, and you're getting this. But in reality, you can fix any two and get the other one. I mean, some of them don't make as much sense. You'd say, I only want to collect 30 samples. That's all I have money for. Then you could figure out, so if you only had money to collect 50 samples and I want to be 99% right, then your confidence interval is determined at that point. However, if you say I can only collect 30 samples, that's all I have money for, and I only want to be 2 units off, then your confidence is set at that point, and so on. Okay. All right, so let's look at this. So this kind of like showing that. So in the book, you need to get that value. But if you're just looking it up, if you're using Excel, it does the lookup of the statistic for you. Okay. All right, this is another way to diagram what I showed in the Python workbook earlier. What this is showing you is these were all of the individual samples taken from a sample population. It could have been the same exponential one that I took. So these are the min, the max, and the sample mean. Here's the sample mean right here. Or sorry, not the min, the max. These are all the sample means, and these are the confidence intervals. They're all the same size because the confidence interval will be the same for all of them. But notice that one time it didn't include, 1 time out of 10 it didn't include. So it's a way to show you how 1 time out of 10 it's not gonna hit the real population value. You're gonna make a mistake 1 time out of 10. The probability of making an error is 0.1, 1% of the time, 1 out of 10 times. All right, so the conventional way to do this is by looking at t-tables. Your z-tables, so once you figure out your z-score, you can look at the table and figure that out. Or you can use the Excel chart to do that. So this is just showing you that you're looking for this area under the curve. Okay. So these are just definitions. We've covered these. The confidence level is the probability that the interval surrounding the sample mean encompasses the true population mean. It's defined as 1 minus alpha. So sometimes you're actually wanting, in fact, the way Excel requests it is in terms of alpha, not in terms of this. See, that's the reason why I had to do 1 minus C7. So Excel wanted the probability that the probability that I was going to make a mistake, and the confidence level is the probability that you're correct. And based on what we talked about earlier, it's just one minus the other. Okay. All right. Now the significance level is alpha divided by 2, the probability that the interval surrounding the sample mean fails to encompass the true population mean. Significance is denoted by alpha equals the total sampling error. Okay. So the confidence interval is just calculated as z. That's the way it's calculated. The standard, the distance away on the standard distribution times, what you're doing is you're just scaling it up to your distribution times the standard error, which is the standard deviation divided by the square root of the number of samples. So that'll allow you to calculate the mean plus or minus the interval as a z-score. And then remember to look at and see if you need to use the finite population correction. If you do, it's just a multiplicative term. You multiply this value by the finite population correction value. In statistics, we often use 99, or 0.99, 0.95, and 0.90. Those are the most commonly used confidence intervals. Okay. Higher confidence intervals result in wider intervals. So there's less precision, but there's a lower amount of error. In other words, you're not making a mistake as often. So, the secret is, for any project, you need to decide what the level of error is and balance the level of error, and then determine how many samples you need, or so on. Okay, so here's a real world. In the real world, notice that we have this population standard deviation. That's one of the terms. In the real world, we don't usually have the population standard deviation. That's not a known number. Okay, so how do we estimate the standard error if we don't have the real world standard deviation? Well, we can use the sample variance, which is the standard deviation squared. That's an acceptable approach. So in other words, we can take the sample standard deviation and square it, and we can use that number in there. All right. Now, if we need to use the with the finite population factor, that's just multiplied in there. So another way to calculate this out, we can rearrange these n's and n minuses. See how this says n minus 1? Well, if this is the sample, then we rearrange that and we just use that value right there. Okay. So that's standard deviation squared divided by n. Okay. All right, now what if the sample size is smaller than 30? Well, if the sample size is smaller than 30, we can use the t-distribution. The t-distribution will account, basically what it does is it accounts for the differences. There is a t-distribution table in the back, there are two of them, in the back of the book. So instead of using Z, you're using the little t here. So you could see that the t value for, well, what was the one we checked before? For 0.90. So if we look at 0.90 and we look at infinity, we get 1.64. It's really close to 1.65. They're almost the same. Okay. But see how that number changes as we go down. That z is going to get bigger. It's going to force our confidence interval wider. So if we only had 5 and we're still looking at a 0.90 level of confidence, the t value would be 2.02 rather than 1.64, which would result in a bigger number. So we could do that here. So I'm going to just create a new table over here and say this is going to equal confidence. There's a confidence t. See that? Confidence t. And I could say the alpha, again, is going to be 1 minus the confidence level. Okay. And the standard deviation is this. And the sample size is that. Oh, not the sample size. The sample size is this. Okay. See how those numbers are pretty similar. That number is pretty similar. It's not exactly the same, but it's pretty similar value. So I'm going to double that just to show you what the width would be. Whoops. Times 2. And then the lower bound is going to equal this minus that. And the upper bound is going to equal this plus that. It's the way it always is. Okay. Now, the difference here, another difference between in Excel, between using this confidence.t and the confidence.norm, is the confidence.t always assumes that this is actually the sample standard deviation. So use confidence t when you're like doing the homework and it says you're trying to find you don't have the population standard deviation. You only have the sample standard deviation. Okay. So that's why this number is a little bit different, because you're using this is basically using this formula to come up with this, rather than just assuming that we know it, which is what this is doing. This is saying, I know the population standard deviation. This is saying, I don't know the population standard deviation, so use that formula to estimate it, and that's why this is ever so slightly a different value. Now, all the rest of the same thing will happen. As the samples increase, we'll get different values. As they decrease, we'll get different values. What happens if we make the sample size really small? What does that do to the confidence interval? It makes it a lot bigger. See that? Okay. And notice that these really start to separate. See how big they are? The differences are now? What's the difference between the lower bound here and the lower bound here? That's pretty big. 6.97, 5.87. That's like well over 1, right? But as we get up, 30, now the difference is only less than 0.1 once we get to 30. And as we get to 100, the difference is now 0.01, right? So the sample size has a big difference on whether or not we're getting close to a true population value. All right. You can play around with those numbers a bit. So yeah, on the homework, use that number to calculate, use that formula. I'll re-upload it because this is not included. But confidence.t is what you want to use. Now, if the finite population correction comes into play, you are going to have to calculate that by hand. Okay, but there's only one example of that in the book. I mean, in the homework. So in other words, if that comes into play, you have to calculate, because this is only looking at the left side of this equation here, not the, doesn't include the finite population correction. Okay. So this is saying, what if the sample size is small? If sample size is small, you use the t-distribution. As it gets close to 3, we just saw they get very, very similar. Sorry, 30. They get very, very similar. So above 30, you can use either one, really. It'll give you almost the same answer. Yeah. All right. Okay. Now, to calculate a confidence interval, we may or may not get through all this part here, but that only works if we can assume randomness. Okay? And in a lot of cases, we can, but not assume, if we actually had a random sample. If our sample was stratified, though, particularly if it was stratified disproportionately, then we need to calculate our confidence interval in a different way. It's kind of like we need to come up with a weighted confidence interval, because the numbers are going to be different. Okay. So, yeah, this slide just showing if we want to estimate the population mean, that's the one we already covered. Okay. So if it's random or systematic, we use this one. This is the one we covered. That's how we create the confidence interval. So the point estimate is the sample mean. The confidence interval is constructed by using z or t, and then multiplying it by that formula, or just using Excel, and this is the formula Excel is using. Okay. All right. But Excel only assumes that you've got an infinite population. So if you do need to use the finite population correction factor, then you'll need to use the book. So but this formula is pretty easy. Take the sample standard deviation, square it, divide it by the number in the population, and then divide that by the ratio of the total population divided by the sample population divided by the total number in the in the sample population. Okay. So, but what if we wanted to make an estimate of the population total? Well, the population total is calculated as the z-score times the total number in the population squared times the standard error. That's what that is. That term is the standard deviation squared divided by the sample count times the finite population factor if it's necessary. Finite population correction factor if it's necessary. Okay. So when would that happen? Well, it's less often that we'd want to do this, but what if we wanted to calculate the total number of people that we're going to vote for Donald Trump, not the proportion of the number of people that we're going to vote for Donald Trump? And we took a sample. Okay. So the big N there would be what in that case? It's the total number in the population. So what's another way to say that? In this case, the total number of voters. So what we're saying is the total number of voters squared divided by the sample standard deviation squared. Multiplied by the sample standard deviation divided by the number in our sample. So if we only sampled 10 people, we divided by that, and then multiply it by this ratio. So that would be something like, millions of people, hundreds of millions of people, right? Or the number of voters. Okay. And then the last estimate that we might want to come up with is the estimate of the population proportion. Okay, so the best estimate of the population proportion is the sample proportion, and then you put that in into a formula like that. This is actually a really simple formula. So if the proportion of people said that they were going to vote for Donald Trump in our sample was 50%, or let's not do 50, was 60%, it would just be 60 times 40 divided by the number of samples minus 1. Okay. And if we could assume it's an infinite population, we didn't need a finite population correction factor, that would be it. Take the square root of that value, multiply it by 1.96, and then we get our plus or minus. All right. Now, it gets a little tricky if we end up stratifying our sample. That's the biggest way we can make it not random, is to the biggest way we can make it not random is to disproportionately stratify it, and then we need to do the correction for that, and that does get into some kind of big, little bit more complex math. I should probably make a spreadsheet to get you started on it. It's not like horribly complex math. We're still talking about sums and multiplying, okay? But I will do that. So let's use the rest of our time, since we only have about 8 minutes here, to see what you guys should do for your homework, and we'll talk about stratified sample means next time, and we'll show an example, so that might be a little bit easier to do. I'll prepare a spreadsheet for it. Yep. And then the last thing here is sample size selection. Okay. We may cover this next week, but if we don't get to it really quickly, these formulas are pretty simple. We're just talking about finding out how many samples we need given a certain confidence interval. Okay. We could already kind of do that. Like, let's say we want the confidence interval to only be 2. Let's say we want the confidence interval to only be 2 units wide. Well, one thing we could do is just play with this, right? We could just go 60. Yeah, okay, so that's going down. 40, 30, 20. Oh, 20 is too big. 25 and 28. Nope. Anyway, we can keep playing with it until it equals 2. Okay, but we can rearrange the math to do it a different way. And that's what these last few slides are talking about. So this is a sample size selection for whether or not you're doing proportions or totals or the mean, which is the most common one. So basically n is going to be equal to the z-score for let's say it's 90, that's 1.96. 1.96 times the sample variance divided by E, which E is this value right here, and then you just plug that in there, and you get your value. We can go over that. We can actually do another example of that next week too. But I want to really quickly see where we should be, because there are a few questions that ask for the stratified stuff. Am I on the wrong class? No. Okay, so that's this one. So you should be able to do all of Chapter 7. And for Chapter 8, what you should do is you should definitely do this part, because it has nothing to do with stratified sampling. So do this one. This one is from Excel table. If you open up the Excel table right here, the workbook table, and it is it's the one, Chapter 8, central limit theorem. Okay, so this is basically doing kind of what we did, but a little bit more by. So we're calculating we've calculated the sample average for you. So these all represent a number of samples. Here's the sample average. Here's the sample standard deviation. Here's the confidence interval, and there's the confidence interval. There's the upper and lower value and the sample size. So what you're going to do is you compute the mean and the standard deviation for both samples. how do you calculate the mean of all the sample size 40? Which column do I need? A, B, C, D, E, or F? I want to calculate the average, the mean. That's another way to say that. It's this column right here. You're going to calculate the mean of that column. That number is going to go right here. Then you're going to calculate the mean of all these data that only had 5 samples. Okay. So you're going to have an average of all the 5 and all the 40. Actually, it's going to be the opposite of what I said, right? The 40 was on top, so that's going to go there. And then the standard deviation is not the average of this column. Okay? Standard deviation is the standard deviation of these values. All right. So then, what is
So the standard deviation of the numbers in the average column?
Yeah. So then you're going to compute the theoretical standard error based on that. Okay? Compute the mean and the standard deviation for both groups of samples. So the standard error is just going to be, you're going to use the formula. You're just going to use this formula. Once you get those numbers, I went way too up too high. Where's the formula for there? You're going to use that formula. That's the standard error. The variance divided by the number of samples. So that value divided by the square root of n, which is 50 or 40 in this case. Okay, so it's 50 or 40. This time it's 40, that's 50. I mean, sorry, 5 or 40. Okay. Then you're going to compute the 90% confidence interval, which has actually already been computed. I don't know why they said that, but that's already there. See that? Like that's already in the book. That's already there. The confidence, the upper and lower confidence intervals, and you can see how they've been calculated. How have they been calculated? Well, they used z, which was 1.65, times the standard deviation value for the sample standard deviation value divided by the square root of 40. Why 40? That's this number. And so these are saying divided by 5. Okay. So so you got the upper and lower bounds for each of the 50 samples, and then yeah, so you've got those values. So then what you're going to do is you're going to calculate how many times this value goes. How many times that interval contains this average value. Okay, so how many times should it? In other words, the sample average should be the population mean, right? The mean of all these should equal the population mean. So theoretically, this confidence interval, since we said 90% of the time, the true population mean should fall inside of that value. How many times should it fall in if we have, how many do we have? I know that we just kind of ran out of time here, but how many do we have of 40? We have 51 times, right? Or 50. So there are 50 of these. So 90% of the time, the average of this column should fall within that value based on theory. So you're going to figure out how many times it does fall into that column. Yeah, that's,
Very classic.
yeah. So, like, I don't know what number you're going to get, but let's say you get 123. So you're going to find out, does 123 fall in this? Yes or no? Yes or no? Yes or no? Yes or no? Okay? So a bunch of yes or no. So you're going to get one value, and you're going to find out if it works. And that's what it's asking you. So theoretically, how often should it happen? Well, it should happen 10% of the time. So 10% of the time is once out of 100, but you only got 50. So how many times did it find? It's probably going to be 0 once or twice that it happens out of 50, right? But you're gonna find that out, and it's going to ask you. We say it idealized because, it's supposed to happen 9 out of 10. Sorry, not 1 out of 100, because we did 0.90. So it's actually 10 times out of 100. Okay. All right. But anyway, it's not going to be the number you think. It's not going to be exactly the number you think it's going to be. It's going to be slightly off. Why? Well, it's because it's a sample. It's not like it happens every time. It's the law of averages. So if we did it like billions of times, we would expect it to be the exact right number. But if we're just doing 100 or 50 times, it's not going to be the exact right number. So basically, it should be 5 out of 50 times it should happen, 1 out of 10 times. 90% confidence interval, 9 out of 10, or another way to say that is 1 out of 10 that doesn't happen. Okay? So what percentage actually contained the population? Why don't you think it was exactly 90%? So you have to answer that. So you can do that. Now, this part, though, you won't be able to answer. Okay. You won't be able to answer this part. So just hold off on, we'll do the second part of the homework after I show an example of how to do that. Okay? All right. I don't know why my daughter just called me twice, so I guess I should figure out why.
Yeah.
So I'll
Absolutely.
I'll go figure that out. And
Fall to the room, you're not an emergency.
yeah. So anyway, it is time in class. It's the right time, and.